You ever just stop and think about it? That little blue dot on your phone? I mean, it feels like magic, right? Well, it kind of is. But it's a magic that's built on a wild symphony of satellites, hyper-accurate atomic clocks, and, believe it or not, even a little bit of help from Einstein. So today, we're going to pull back the curtain and figure out how this invisible science in your pocket actually works.
I mean, it seems so simple. You pull out your phone, open a map, and bam, there you are. But here's the thing a lot of people get wrong. Your phone isn't talking to the satellites. There's no back and forth conversation. The truth is, your phone is just a silent listener, catching these faint signals from a whole constellation of satellites whizzing by 20,000 kilometers over our heads.
All right, so here's our game plan for this explainer. We're going to start with a kind of cosmic treasure hunt using some basic geometry. Then we'll get into how we can measure huge distances just using time. We'll uncover the secret job of a fourth satellite, tackle a truly mind-bending problem solved by Einstein, and then we'll see how all of this is way, way bigger than just that blue dot.
So, first things first. How in the world does the system even start to find you on a planet with a surface area of over 500 million square kilometers? Well, the answer isn't some super complex algorithm, it's actually a really elegant geometric trick.
And the key word here is trilateration. Now listen, this is super important. It's not triangulation. You've probably heard of that. It uses angles. We're not doing that. Trilateration. It's all about measuring distance. You can think of it like you're on a massive treasure hunt, and the clues are just how far away you are from a few known spots.
Okay, so check this out. It's wild how fast this narrows things down. One satellite signal comes in. That tells you that you are somewhere, anywhere on the surface of a giant imaginary sphere. Okay, not super helpful. But then, a second satellite signal comes in, and where those two spheres overlap, they form a perfect circle. Now we're getting somewhere. Add a third satellite, and its sphere slices through that circle in exactly 2 spots. Okay, we are so close.
So you're left with 2 possible points. How does it know which one is you? Well, it's actually pretty clever. The Earth itself basically acts as a fourth giant sphere. See, one of those 2 points is going to be you, standing on the ground. The other one, it's going to be some ridiculous location thousands of kilometers out in space. So the system just throws out the one that makes no sense, and bingo, it's found your latitude and longitude.
Okay, hold on a second. This brings up a huge problem. That whole geometry trick is completely useless if we don't know the most critical piece of the puzzle, our exact distance to each of those satellites. I mean, how do you even measure that? You don't have a giant cosmic tape measure. The solution is just beautiful. We know radio waves move at the speed of light, right? It's like the universe's ultimate speed limit. So all your phone needs to do is figure out exactly how long it took for the satellite signal to travel to you. You just multiply that travel time by the speed of light, and bam, you've got the distance. Simple as that.
Now, obviously for any of this to work, the timing has to be, well, perfect. Absolutely perfect. That's why every single GPS satellite has an atomic clock on board. These things are insanely accurate. With every signal it sends, it includes a timestamp of the exact moment it was sent, right down to the nanosecond. But that incredible precision, it actually sets up the biggest problem in the whole system. And here it is. The single biggest problem. And you know what? It's not in space. It's right there, in your hand. The satellite has this ridiculously precise atomic clock. Your phone, it has a cheap little quartz clock. And the difference between them is just staggering.
I mean, just look at this. You've got a piece of lab equipment that costs $100,000 on one side, and a component that costs a few cents on the other. There is no way, I mean zero chance, that your phone's clock is as accurate as the satellite's. It is guaranteed to be wrong. And that little time difference, that offset, should make the entire system completely fall apart.
And this is where things get crazy, because light moves so unbelievably fast, about 300,000 kilometers every second, that even the tiniest little hiccup in timing creates a massive error in distance. If your timing is off by just 1 nanosecond, 1/1000th of a second, boom, your location is wrong by about a foot. In your phone's clock, it's off by way, way more than that.
So, if your phone's clock is basically junk, how on earth does GPS work at all? It seems impossible, right? Well, this is where the real genius comes in. Instead of trying to give you a better clock, the system just says, okay, we know your clock is wrong. Let's just figure out how wrong it is. It treats that time error in your phone as just another puzzle piece, a fourth unknown variable we need to solve for.
And that is the secret job of the fourth satellite. This is so cool. Remember, we needed 3 satellites to figure out our 3 dimensions in space.
X, Y, and Z. That fourth satellite gives us the extra piece of information we need to solve for the fourth unknown, T, for time. Its job isn't geometry anymore, it's algebra. It lets your phone calculate exactly how off its own clock is and then correct all the other distance measurements. It's this absolutely brilliant hack that means you don't need a $100,000 atomic clock in your pocket.
Okay, so we're good, right? Geometry solved, clock problems fixed. We're done. Except we're not. There's one more layer. One final mind-bending problem rooted in the very fabric of space and time itself. And if we didn't account for it, GPS would be off by 10 kilometers every single day.
This is where the ghost of Albert Einstein enters the machine. His theory of special relativity tells us something really weird. The faster you go, the slower time ticks for you. And those GPS satellites are absolutely screaming through space at 14,000 kilometers an hour. Because of that insane speed, their onboard clocks actually run just a tiny bit slower than ours do down here on Earth.
So what does that mean in real numbers? Well, from our point of view, those satellite clocks lose about 7 microseconds. That's 7 millionths of a second every single day just from their speed. But that's only one half of Einstein's story.
Because Einstein also gave us general relativity, which tells us that gravity actually warps time. The stronger the gravity, the slower time passes. Since the satellites are way up there, 20,000 kilometers high, they're in a much weaker gravitational field than we are. And guess what? This does the exact opposite thing. It makes their clocks tick faster than ours.
And this effect from gravity, it's way bigger. Because of the weaker gravity, the satellite clocks actually gain about 45 microseconds every day compared to us on the ground. So now you've got these two effects from relativity fighting each other.
All right, so let's do the math. You've got two forces battling it out. Gravity is making the clocks run faster by 45 microseconds a day, but their speed is slowing them down by 7 microseconds a day. So you put it all together, and the net result is that every satellite's clock gets ahead of our clocks on Earth by 38 microseconds every single day.
So, 38 microseconds. Sounds tiny, right? Who cares? Well, you should care, because that tiny time drift adds up to a positioning error of more than 10 kilometers a day. Your GPS would be completely useless in less than 24 hours. Without Einstein, there is no GPS. Period. The engineers actually account for this by building the clocks on the ground to run just a little bit too slow so that once they're in orbit, relativity speeds them up to the perfect rate.
So there you have it. We've wrestled with geometry, we've hacked the problem of time, we've even dealt with Einstein's ghost in the machine. But the story of GPS and its impact goes so much further than just helping you find the nearest coffee shop. You know, this whole thing started as a US military project called Navstar, but now it's literally the invisible heartbeat of our whole world. That super precise timing signal from the atomic clocks, it's used to timestamp billions of financial transactions. It keeps our power grids and cell networks perfectly in sync so they don't collapse. In fact, your phone today probably isn't just listening to the American GPS system, but also to other systems, like Russia's GLONASS, to get an even better, more reliable lock on your position.
So really, the next time you pull out your phone and see that little blue dot just pop up on the screen, take a second. Think about those invisible spheres, the clever algebra of the fourth satellite, and Einstein's theories correcting space-time from thousands of kilometers away. It really makes you wonder, right? What other invisible magic is all around us, just making our world work?